So, in the last classes we have discussed about the BJT being applied as an amplifier, that is the amplification of a weak signal is done by a BJT, and the analysis for the amplification or using the BJT as an amplifier we have discussed in details. Now, apart from using the BJT as an amplifier, we have other use for a BJT also, and that is a switch. That is, a transistor can be operated as a switch also. Now, when a transistor is used as a switch, means that it can be used for opening or closing of a circuit, and when the transistor is operated in this manner, then it is not used in its active mode of operation, but it is used in saturation mode and cutoff mode of operation, because we know that the transistor is having three modes of operation: active, saturation and cutoff, and in the active mode of operation the transistor is mostly used as an amplifier, but for some specific applications as in a switch we use the other two modes of operation, which are the saturation and the cutoff modes. So, today we will be discussing about these two modes of operation and see how the transistor uses these two modes for being applied as a switch. Now, the application of transistor as a switch has found use in many areas, like in computers and control applications. The BJT is used as a switch, and one typical example can be cited where a BJT is used as a switch in digital circuits. For example, in an inverter, that is, inverter is a device where the output will be just the inverted form of the input. For example, if we give a low input at the inverter, then the output will be having high, and if the input is high, then output of the inverter will be low. So, the circuit for the inverter is as shown in this circuit. Here the BJT common emitter is used, and the resistances in the collector as well as in the base are RC and RB, and VCC is the biasing voltage that is having, for example, in this case we are taking 5 volt VCC, and the values of the RC and RB are 0.7 k ohm and 50 k ohm. This is a very simple example, and the beta value for this common emitter transistor is 125 say. Now, input is Vi, that is being applied to this transistor amplifier, and the output at the collector side is Vc, which is nothing but Vce, because here emitter is grounded. So, the voltage between collector and emitter is the voltage with respect to ground at the output side. Now, the input to this transistor circuit here is given as shown here, that is, it is between 0 and 5 volt, which is given at the input. Now, mind it that we do not have a DC biasing voltage here, but we are using a time varying signal between 0 and 5 volt at the input of this transistor. Now, what will happen to the voltage at collector, that we are going to see. That is, when you have voltage 0, Vi 0, what will be the output at collector, what will be Vc, and when the voltage is 5 volt, what will be the output Vc, that we have to find out. For this particular example with these typical values, let us see what will be the output voltage at collector. And to see that, we have to again revisit the characteristic of the transistor. Let us recall the output characteristics of a common emitter transistor. And we know that in a common emitter output characteristic, when the voltage VCC that is given is equal to the voltage at one extreme point of the characteristic curve and the other extreme point of the collector current that we are having are joined by a straight line, we get the load line. For this particular example, let us find the load line and draw it on the characteristic curves. For that, we have here the voltage VCE equal to VCC minus IC RC. Now, when IC equal to 0, VCE is equal to VCC and that will be equal to 5 volt. So, one extreme point of the load line, and when VCE equal to 0, we get IC equal to VCC by RC, the other extreme point of the load line. So, in this particular example, the value of IC max will be equal to VCC by RC. VCC is equal to 5 volt, RC is equal to 0.7 K. So, that will give 7.1 milliampere, that is the value of the saturation current IC sat. And when IC equal to 0, VCE maximum value will be 5 volt VCC value here. So, we are joining these 2 points and this is the load line for this particular example. Now, in this plot, we are now having the output characteristics, that is the curves for different values of the base current. Now, base current is from 0 onwards. So, we are plotting for IB is equal to 0, for IB is equal to 10 microampere, 20 microampere, like that, and the values of IC in milliampere are on the y axis. Now, the saturation voltage VCE sat, that saturation voltage is almost equal to 0, that is assumed here. Practically, the VCE saturation is the saturation value of the collector to emitter, and that is around 0.1 or 0.2 like that. That means it is a very small value. So, for simple analysis, we are assuming that VCE saturation is equal to 0 volt. That is when we have IC saturation flowing maximum collector current, then VCE is equal to 0. And the cutoff value of current, that is ICEO, this current is actually the reverse saturation current when the base current is 0, that is base current is IB is 0. So, we know that the value of IC is actually beta times of IB plus beta plus 1 into ICBO. But if we make this IB equal to 0, we have IC equal to beta times of IB plus beta plus 1 into ICBO. Now, if IB is equal to 0, IC is equal to actually beta plus 1 into ICBO. ICBO means the reverse saturation current IC naught. But for simplicity, we are assuming that this part is 0 for IB is equal to 0. That means, when the base current is 0, the reverse saturation current is very small. So, this part is also almost equal to 0. That is why we are writing ICEO equal to 0 milliampere when IB is equal to 0, and that is shown by this axis itself. So, that is why this is ICEO equal to 0 when IB is equal to 0. Now, with this knowledge, now let us proceed to see the circuit again. So, the current that flows in the circuit under saturation condition is IC saturation, which is 7.1 milliampere, that is the maximum value of the collector current under saturation, and correspondingly the value of the base current will be IC by beta, and IC is equal to 7.1 milliampere saturation current divided by, for this particular example, beta is 125. So, that gives 56.8 microampere. So, if IB is equal to 56.8 microampere and more, the condition of the transistor is in saturation, because we can see here this is the peak value or maximum value that the collector current can have in this circuit when VCE is equal to 0. So, that is equal to 7.1 milliampere, and for that collector current, what will be the corresponding base current for which this collector current flows? That is 56.8 microampere. Now, if base current is increased beyond 56.8 microampere, then the transistor will be into saturation. It will be overdriven and the saturation condition will occur. That means, beyond this IB is equal to 56.8 microampere, the transistor will be achieving the saturation condition. And when the transistor is in saturation, we know that the collector to emitter voltage will be 0. So, the saturation to happen, the condition is that the base current is more than IC saturation by beta or 56.8 microampere in this particular example. So, if we give an input voltage and we adjust the resistance in the transistor RB, RC, etc., such that the base current becomes more than 56.8 microampere, then the transistor will be driven into saturation, and then the voltage which will be at the output or collector, that Vc will be equal to 0. So, now in this particular example, what we are applying is a voltage between 0 and 5 volt input voltage. Now, what will happen when you have a 5 volt as input? Let us consider the case when input voltage is 5 volt, because it can be 0 or 5, it is a pulse. It can have two values, either 0 or 5 volt. It is a digital type of voltage. Now, if this voltage is 5 volt, input voltage is 5 volt, in this circuit the voltage which will be at Vc or at the collector, that is Vc, we have to find out. Now, when the voltage at the input is 5 volt, then what will be the base current that can be found out? By applying Kirchhoff's voltage law, Vi minus Vbe divided by Rb, which is 50 kilo ampere. So, 50 kilo ohm. So, what will be this base current? Base current is equal to Vi minus B base to ammeter voltage divided by Rb. So, putting the values of this in the equation, we can find out what is the base current. 5 is the input voltage, minus 0.7 volt is typically the value for VBE for a silicon transistor. We are assuming that, divided by 50 kilo ohm is the resistance Rb. So, that gives 86 microampere. That means 86 microampere base current is flowing when you have input voltage 5 volt. So, that is well above the value of IB which is required for saturation, because saturation requires IB value for 56.8 microampere. So, whatever we are getting here, IB is much greater than 56.8 microampere. So, the transistor is driven into saturation. So, the output voltage VCE or the voltage at the collector Vc will be equal to 0. So, when you have an input 5 volt, output becomes 0. Now, when we will be having a voltage Vi is equal to 0 volt, that means the other condition of the input voltage, let us examine. And for that, here if input voltage is equal to 0 volt, then the base current will be 0, because if we look into the circuit, if this is 0, the emitter is grounded, which is also 0. So, the emitter base junction is not forward biased, which is the condition for the transistor being on. That means, if we do not have that emitter base forward bias, in this particular example it is NPN. So, P must be having a higher voltage with respect to N, that means we must have base voltage greater than the voltage at the emitter, which is not happening, because if it is Vi is equal to 0 volt, this is 0, this is 0, both are same. So, we are not having base at a higher potential than this emitter, because this is an NPN transistor. We must have forward biasing, which is not met, and that is why there will not be flow of base current. That means base current is 0, the transistor is not on, it is off. So, when base current is 0, then collector current is only the reverse saturation current, and here we have assumed that the reverse saturation current is also 0, and that is why we are getting at the output the voltage which is equal to 5 volt, because output voltage is equal to Vcc minus Ic into Rc. Now, Ic is equal to 0, since Ib is equal to 0. So, we are getting Vc equal to Vcc, that is equal to 5 volt. So, that means when input voltage is 0 volt, we are getting at the output 5 volt. So, if we now compare the two voltages, input and output voltages Vi and Vc, then we get the plot like this. That means, when you have input voltage 0, the collector voltage is 5 volt, when the input voltage is 5, the voltage at the collector becomes 0, it is just inverted. So, if it is low, it becomes high, if it is high, it becomes low, and this is the action of an inverter. An inverter is actually, this is the symbol of an inverter. If it is 0 at the input, output will be 1, if it is 1 at the input, output will be 0. This is a digital device, and in digital circuits, the voltage is in between two levels, and it is typically between 0 and 5 volt. That is why in this example we have actually analyzed the circuit of an inverter, and we have seen that here the transistor is operating in two modes. One is in saturation mode and the other mode is a cutoff mode, and when the transistor is on, this is in the saturation mode, and we are getting at the output the voltage, the collector voltage, which is equal to 0. But when it is in the cutoff mode, the transistor is in cutoff, means we are having the output voltage equal to the voltage which is equal to 5 volt, and this is the cutoff mode of operation. So, in between saturation and cutoff, the transistor is operating, and if we now also look into the transistor when it is operating in saturation and when it is operating in cutoff, we can see that these actions are nothing but the actions of a switch, because again if we consider the transistor under saturation, this is the transistor symbol where we are using here a common emitter transistor. Suppose it is the condition when it is operating in saturation, then Vc is saturation, which we have seen that it is almost equal to 0, and practically this value may be either 0.1 or 0.2, but very small. So, we are assuming almost equal to 0, and the current flowing in the transistor under saturation is Ic sat. So, symbolically we can equivalently we can express it as a switch between collector and emitter, because it is like a short between collector and emitter as if it is being shorted by a switch, and what will be the resistance from collector to emitter? The resistance between these 2 points or 2 terminals, collector and emitter, is nothing but the voltage by divided by the current, and voltage between collector and emitter is VCE sat, and the current flowing from collector to emitter is the saturation current ICE sat, and this VCE sat is equal to 0 volt, ICE sat is equal to IC sat has a of course high value, but it does not matter because in the numerator if it is 0, resistance becomes 0. So, the resistance of this part between collector and emitter is 0 ohm. So, if the resistance is 0 ohm, that means it is like a short, and this is the action of a switch. A switch is on, means the current flows without any resistance or 0 resistance. So, as if the collector to emitter part is being closed by a switch which happens under saturation. So, this is the saturation condition, that is why we can equivalently say that this is working as a switch which is on, that is the switch is on, means it is in the saturation. Now, in the other condition, when it is in cutoff, then the voltage between collector and emitter is VCC, which is in this particular case is 5 volt, and the current which flows in the collector, that is the ICEO, and we have assumed it, and this is practically correct, that it is almost equal to 0 milliampere. So, what will be the resistance between these 2 points, collector and emitter? That will be equal to 5 by 0, almost infinite, that is infinite resistance is offered by this part between collector and emitter when it is in the cutoff mode of operation. So, the switch is like it is now open, because you see that we do not have any current, 0 current is flowing, and the resistance between these 2 points, collector and emitter, is infinite. So, infinite resistance is being offered by this part between collector and emitter. So, there is no current and it is like an open switch. That is why on the cutoff condition, the transistor can be well assumed to behave like an open switch. So, this analysis now shows us that we can use the transistor in these 2 modes of operation of saturation and cutoff to close a switch on or close a switch off. Now, for example, if these values of this saturation voltage VCE sat is not 0, even it is a few order of say some 0.1 or 0.2 volt, then also the resistance which will be offered, it will be almost like 0, it will be very small value, because IC saturation is a high value. So, this whole quantity will be almost equal to 0, even if it is not 0, it will be very small. And in the other case, when cut off, in the reality, if this ICEO, even if it is not 0 milliampere, it is say 10 microampere, it can be, because it is in the microampere order only, still this value of resistance will be very high. So, it is almost like infinite that we are assuming. So, even if it is a practical case, if you take having not 0 saturation voltage or not 0 reverse saturation current, then also the analysis will not be different, because the order of the resistance value will be almost in the same order. Now, let us again discuss another circuit like the circuit which we have discussed now, which is used for saturation and cutoff, and try to see if this amplifier circuit is also acting as a switch. Now, in this example, we are taking VCC is equal to 10 volt, and the resistances RB and RC are not known. We have to determine the value of resistance RB as well as resistance RC for this transistor inverter if the collector saturation current, that is IC sat, is given as 10 milliampere and the input voltage is between 0 and 10 volt as is shown. So, in this case what will be the value of RB and RC, that we have to design. So, for solving that, as we are given that the IC sat is 10 milliampere, we can find the expression for IC. What is IC in this particular configuration? IC is VCC minus VCE divided by RC, that is generally the expression for the collector current. So, under saturation what will happen? Let us draw this circuit again. Solution for this example, we have a VCC equal to given as 10 volt and we have RC not known, we have to design this RC value. This is a common emitter transistor, it is NPN as per the symbol, and we have a resistance at the base which is RB and input voltage is given as Vi and emitter is grounded. This is the circuit, and here given is beta which is equal to 250, beta value is 250 and input voltage is between 0 and 10 volt. So, this is initially it is 0, then it becomes 10 after some time. So, this is the input voltage across time VIT. Now, what is this saturation current IC sat? That saturation current can be found from this equation for IC, which is nothing but VCC minus IC into RC divided by VCC minus IC into RC minus VCE is equal to 0. That is the original expression for or the Kirchhoff's voltage law being applied in the output circuit. But now, for the case when you will be finding out IC saturation, that can be found out when VCE is equal to 0, make VCE is equal to 0, then IC sat is obtained which is equal to VCC by RC. Now, in this particular case we know IC sat, this is given as 10 milliampere, IC sat is 10 milliampere, and what will be the RC, that can be found out first. So, RC equal to VCC by IC sat. So, VCC is equal to 10 volt, IC sat is given as 10 milliampere, that means it is 1 k ohm is the collector saturation current, that is IC sat. Now, if we know this IC sat, we can find out what is IB for that particular IC sat, and that is IC sat divided by beta. Beta is given as 250. So, 10 milliampere by 250, that comes to around 40 microampere is the value of the IB for which the saturation occurs. If IB is above this value, then the transistor will be driven into saturation. So, now we have to have a condition where IB is greater than 40 microampere to ensure saturation. Now, here as we have to design RB for ensuring saturation, let us assume a saturation current of IB which should be more than 40 microampere, and conveniently let us choose IB is equal to 60 microampere. I am choosing a value higher than 40 microampere, and that range I am taking as 20 microampere, it is higher than 40 for convenience. So, to ensure saturation I must have a value of IB conveniently higher I am taking, and that value I am choosing as 60 microampere which will ensure saturation. Now, if IB I have chosen to have 60 microampere, what will be the corresponding value of RB, that I can find out, because the value of IB in this circuit, this is the IB. So, what is IB in this Kirchhoff's voltage law being applied in this input circuit? VI minus VBE divided by RB, that is IB. So, IB is VI minus VBE divided by RB. Now, we do not know RB, we have to design our RB, and we are designing for a value of IB is equal to 60 microampere. So, for this case, what will be the value of RB? RB is equal to VI minus VBE divided by IB, and VI is 10 volt when saturation will occur, 10 volt. Voltage is given because voltage is between 0 and 10, 0 will make it cut off and 10 volt will drive into saturation. So, we are considering saturation, and that should be then 10 volt input voltage, and typical value of VB is 0.7, we are taking that, divided by IB I am choosing as 60 microampere. So, 60 into 10 to the power minus 6, actually this is if we consider it in ampere. So, that value will be, finally we will be getting a value of 155 kilo ohm. Now, 155 kilo ohm RB value is obtained for a value of IB choosing to be 60 microampere. But as we are designing the circuit, practically when we design the circuit, it is better to take the standard values of resistances, because the resistances which we will be having practically in the laboratory or real environment are actually having some standard values, and that is why it is better to choose standard values while designing, because then our designing will be corresponding to the actual design that can be done in the lab environment. So, although we are getting for this particular value of 60 microampere a value of resistance RB which is 155 kiloampere, but let us take a standard value of 150K, because 150K can be obtained in the lab easily. So, we take RB is 150K as it is standard value which is readily available. So, for this RB is equal to 150K, now we can cross verify whether we are getting the saturation condition or not, because then what will be IB is VI minus 0.7 divided by RB, and for this particular value of resistance which is 150K, VI being 10 volt. So, that value of IB comes to 62 microampere, and so it is well in saturation, because saturation requires that value of the IB current should be 40 microampere or more. So, it is 62 microampere, it is greater than 40 microampere which we got initially as a condition for saturation. So, saturation is guaranteed in this design, saturation is ensured. So, we have in this design we have designed RB to be 150K and RC was designed to have 1 kilo ohm value. So, this design example shows how to get the values of RB and RC if we want to design a transistor as a switch. Now, we have earlier discussed about the transistor as an amplifier, and we also have seen that the capacitances which are present in the circuit do affect the gains. Now, in relation to that, let us do one example. We have to find out in this circuit the lower cutoff frequency for the amplifier. I am going back to the amplifier again, and I want to do an example which has all the capacitances, and what will be the lower cutoff frequency for that for this amplifier, that we have to find out. Now, in order to solve such problems, first thing is to draw the equivalent circuit in a small signal mode. So, if we now draw this equivalent circuit for this amplifier considering all the capacitances, then in the low frequency region, as we have earlier discussed, the capacitances which will be existing will be the coupling capacitor and the emitter bypass capacitor, and the transition capacitance or junction capacitances of the transistor junctions. These will have no effect in the low frequency region, they will be affecting only in the high frequency region. So, in order to find out the lower cutoff frequency, we have to consider only those coupling as well as the emitter bypass capacitors. So, let us draw this equivalent circuit in the small signal. So, small signal model, we will be having the resistance in series with the applied voltage signal Vs. The coupling capacitor, if we look into this transistor amplifier, coupling capacitors are Cs, Cc, and the emitter bypass capacitor is Ce. Others are as which are present in the mid frequency zone also, that is the potential divider biasing circuit having the resistances R1 and R2, RC is the collector resistance and RE is the emitter resistance. Load resistance, these are already there which are existing in the mid frequency also, but in the low frequency region we have to consider the capacitances extra which are affecting. So, the capacitances will be Cs will be there. Then the resistance Rb I am writing for R1 parallel R2. In a small signal model we have these two resistances in parallel, and the transistor is having the resistance between emitter and base which is beta plus 1 into Re, and the emitter is having resistance Re, and the capacitor which is bypassing it is Ce. And let us draw it more clearly, and the output side is having the current source beta Ib which is the collector current. In this direction collector current will flow, and there will be this resistance in the collector which is Rc. There is a capacitance which is coupling the collector which is Cc, and RL is the load resistance. So, the output voltage is V0, input voltage at this point is Vi, the emitter is grounded through resistance Re and Ce. So, in this case now let us denote the current. Base current is Ib is flowing in this direction, this is collector current. Now, in order to know what is the lower cutoff frequency, as we have seen in the earlier classes, that we have to consider one by one the cutoff frequencies. Now, again in this small signal analysis, in order to find out what is Re, the resistance between emitter and base, we have to again consider the DC equivalent circuit, because Re is nothing but 26 millivolt divided by capital I capital E. So, this is the DC current. So, in order to know the DC current, we have to again draw the DC equivalent circuit. So, the DC equivalent circuit, if we consider, we will be left with VCC, the VCC is 20 volt, and R1 R2 and RE, RC. This is R1, this is R2, RC, RE. VCC is equal to 20 volt with the corresponding values of R1 is 40 K, R2 is 10 kilo ohm, RC is equal to 4 kilo ohm, RE is equal to 2 kilo ohm. Now, this is the DC equivalent circuit, and in order to simplify this circuit, what we have earlier done is that we are drawing the Thevenin's equivalent for the base circuit. That will give us a simplified circuit which can be drawn like this. This is the Thevenin's voltage. We have to find out the Thevenin's voltage. So, from the base to ground, the circuit will be looking like having a resistance RB, and this will be RE, RC, VCC. Beta value is given as 100. So, we have to find out what is Thevenin voltage and Thevenin's equivalent resistance, and we know that Thevenin's voltage is equal to the voltage across R2 between base and this ground. We have to find out the voltage, and that is equal to VCC into R2 by R1 plus R2. So, VCC is 20 volt, R2 is equal to 10 K by 10 plus 40. So, if we do this calculation, we are having 4 volt. So, this 4 volt is the Thevenin's voltage, and similarly we can find out what is RB, that is our Thevenin's voltage, which is the parallel combination between R1 and R2. So, it is equal to R1 into R2 divided by R1 plus R2. Putting the values of R1 and R2, we get 40 into 10 by 40 plus 10, and that gives 8 K. So, now if we know this R Thevenin and V Thevenin and replace in the circuit, we are getting this 10 volt, 4 volt is V Thevenin, 4 volt, and RB is equal to 8 kilo ohm. Others are as it is. So, now RE is equal to 2 K, beta is equal to 100, and the RC will be there, RC is equal to 4 K, VCC 20 volt. So, in this circuit now we can find out the base current, we can find out the emitter current, if required we can find out IC also. Now, what we require is emitter current in order to know small r small e. So, for that, if we write down the expression for IB in this loop, V Thevenin minus IB minus VBE base to emitter voltage minus beta plus 1 IB, that is the expression for IE into RE equal to 0. So, putting the values of the voltage and the resistance and the other things, we can find out the value of the base current. So, for IB taken common, RB we have found out 8, 100 is the value of beta into RE is 2K minus 0.7. So, from this the value of IB will be equal to 0.0157 milliampere, 0.0157 milliampere. So, now if IB is this much, we can find out what is IE. It is beta plus 1 into IB. So, beta is 100 plus 1 into IB is equal to 0.0157 we have found out. So, this comes to equal to 1.586 milliampere. Once we know IE, we can find out RE. It is equal to 26 millivolt by IE, 26 millivolt by 1.586 milliampere, and that comes to around 16.39 ohm. 16.39 ohm. So, 16.39 ohm is the value of resistance Re. Now, if we know this, now we can find out all other required things in the small signal model, because small signal model, if we see here, this was the only unknown, others we have found out. So, now in order to know the lower cutoff frequencies, then we have to first find out the input resistance R in, because input resistance R in, looking into the circuit from the input terminals, what will be the input resistance? RB parallel beta plus 1 Re, beta plus 1 Re, because in mid band region, this is in the mid band region, in mid band, because in the mid band region the capacitance C will be short circuiting, and so this will be bypassed. So, we are left with Rb and beta plus 1 Re parallel. So, that let us find out. So, R in, we will be first of all considering mid band region and find out R in. So, Rb parallel beta plus 1 Re. So, Rb is found out, which is equal to 8 kilo ohm, parallel 1.655 is the value of beta plus 1 Re, because beta plus 1 Re is nothing but 100 plus 1 into Re. Re value we have found out to be 16.39, 16.39. So, this value comes to 1.655 kilo. That is why I am putting this here. If we take this parallel combination, 8 into 1.655 plus by 8 plus 1.655, this is the value of R in the mid band, 1.371 kilo ohm. Now, if this R in is known, we can now find out the lower cutoff frequency for all the capacitances. Then we will be deciding which one is the final lower cutoff frequency. So, lower cutoff frequency considering the CS first, that is the capacitance in series at the input with the source resistance, the capacitance which is in series, that is CS. So, what is the lower cutoff frequency? Low cutoff frequency due to CS, FLCS means low cutoff frequency due to CS, that we have analyzed earlier, and we have seen that this is 1 by 2 pi R effective into CS, and R effective for CS is 1 by 2 pi into R effective for CS is Rs plus R in. That is the effective resistance for the capacitor CS. If we look from the capacitor CS and find the effective resistance, you look from this CS, find out the effective resistance, then we are having in this circuit Rs plus input resistance, because input resistance will be the resistance for this input circuit. So, if we look from this capacitor, we are having Rs and other one is R in. R in is the input resistance for this transistor amplifier. So, effective resistance is that much, and so we replace here by Rs plus R in into CS, and that is equal to 1 by 2 pi. Rs is given as 1, I think Rs is 1 in this circuit, 1 K. So, if Rs is 1 K, R in we have found to be equal to 1.371, and be careful about the units, these are in kilo ohms. So, let us multiply by 10 to the power 3, and what is CS? CS is in this circuit of the amplifier, CS value is 10 microfarad. So, 10 microfarad we will be replacing here, 10 into 10 to the power minus 6 is as it is microfarad. The whole calculation if you do, you will be getting the lower cutoff frequency due to CS as 6.71 hertz. This is the lower cutoff frequency due to CS only. Now, if we consider the lower cutoff frequency due to Cc, so FL Cc, that we have to find out. So, that is equal to 1 by 2 pi into effective resistance due to Cc into capacitance C. So, now what is effective resistance due to Cc? That in order to find that, let us look into the amplifier circuit from Cc. This small signal analysis, if we look from Cc, this coupling capacitor, find out the effective resistance, which is actually a series resistance between Rc and Rl. So, in between Rc and Rl, this series resistance is the effective resistance seen by the coupling capacitor. So, we will be replacing here, which is equal to Rc plus Rl into Cc. So, putting these values, we get Rc value is given as 4K and RL is 2.2, but these are in kilo ohm, and Cc value is 1. You can look into the amplifier again and find out what values are given. Cc is 1 microfarad, RL is 2.2K and Rc is equal to 4K. So, putting these values here, we are finding the lower cutoff frequency due to Cc. So, this value comes to FLCC, that is equal to, finally we get 25.67 hertz. Now, what will be the other lower cutoff frequency? That means due to CE. So, the lower cutoff frequency due to CE, let us find out. So, again it is the lower cutoff frequency due to CE is 1 by 2 pi effective resistance looked from CE. Let us denote that by REF FCE into CE. So, CE value we will be replacing. Now, what is the effective resistance due to CE? If we look into the circuit, or we have already earlier found out that this is nothing but the effective resistance due to CE is nothing but the value of Re parallel, small Re plus beta Rb parallel Rs divided by beta plus 1, and this derivation we have already done earlier. So, we will be replacing this value of R effective resistance, which is equal to Re parallel small Re plus capital Rb parallel capital Rs divided by beta plus 1. Now, putting all these values, we get that is equal to R effective resistance equal to R capital is 2 kilo ohm, 2 into 10 to the power 3 parallel. The value of Re we have found out to be 16.39. I am writing all are in ohms, that is why I am giving 16.39 plus parallel between Rb and Rs, that is equal to 8 and 1. So, parallel between 8 and 1 and divided by beta plus 1. Beta plus 1 is 100 plus 1, and this will be multiplied by 10 to the power 3. If we do this calculation, we will be finding, you can check this calculation and verify, this will be equal to finally 2 into 10 to the power 3 parallel, the whole value of the right hand side of this parallel will be 25.2 ohm. So, the parallel combination between these two will be 2 into 10 to the power 3 into 25.2 by 2 into 10 to the power 3 plus 25.2, and that comes to 24.89 ohm. So, now if this is the value of the effective resistance, now we can find out the lower cutoff frequency FLCE 1 by 2 pi. R effective we have found out 24.89, and CE, the value of CE is 20 microfarad. You can look into the amplifier circuit and verify. It is, I think, true. I mean, it is 20 microfarad. Yes. So, putting these values 20 microfarad, if you place here microfarad, so 10 to the power minus 6 is the factor by which we have to multiply. So, this value comes to 319.72 hertz. So, now we have three lower cutoff frequencies FLCS, FLCC and FLCE. The lower cutoff frequencies are due to the coupling capacitor CS, CC and emitter bypass capacitor CE. So, these values we have found to be equal to 6.71 hertz. The value due to CC is 25.67 hertz and the value due to CE is 319.72 hertz, and this is the highest value. That means, out of all the three, the value due to CE, which is 319.72 hertz, is the greatest value or largest value of the lower cutoff frequency. So, now we have to choose the largest among all the three lower cutoff frequencies, and that will be the finally the value of the lower cutoff frequency for this amplifier circuit, because in the lower frequency region you have to take the largest value among all the lower cutoff frequencies. So, what will be the final value of or the overall lower cutoff frequency FL, I am naming it by FL, is the overall lower cutoff frequency for the amplifier circuit, and that is equal to the value which is due to the emitter bypass capacitor CE, because that is the largest value among all the three, and that is equal to 319.72 hertz. So, finally, this is the lower cutoff frequency in this amplifier. So, mid-band frequency region gives a voltage gain constant, but lower and higher frequencies offer a voltage gain which are reduced, and here in this particular example we have seen that the value where the 3 dB cutoff frequency exists is the value 319.72. So, this will be this type of voltage gain actually we get in the amplifier because of all those capacitances. So, this is the value of the lower cutoff frequency FL, because here at this point the gain voltage gain drops to 1 by root 2 times AV if this is AV. So, out of all these three we have selected this value. So, similarly we can also find out in the high frequency region the upper cutoff frequency for the amplifier. Of course, then we will have to know what are the junction capacitances in the model of the transistor. So, this example just shows the way of calculating lower cutoff frequency. Similarly, we can calculate the upper cutoff frequency for an amplifier in the high frequency region, and if we have a more than one cutoff frequencies, obviously that will be the case if we consider the junction capacitance CBE and CBC, base to emitter and base to collector junction capacitances, then we will be taking the lower among the two. In the high frequency region, when we find out the upper cutoff frequencies, we have to take the lower among the two, but here in this lower cutoff frequency we take highest among the 3. So, in this analysis whatever we have done till now involving BJT amplifier, we have seen how amplification takes place, how to find out all those parameters involved in amplification like voltage gain, current gain, etc. And also we have seen the effect of capacitances which are present in the amplifier, how the voltage gain is affected because of the capacitances, but all the analysis was done considering a small signal, and this analysis is completed as far as BJT amplifier is concerned.